stats. I hope you guys are having a great day. We are moving on to 11.2, and this entire section 11.2 is all about the other two tests for chi-squared. So we already did the chi-squared test, the goodness of fit test. Today we're going to do the test for homogeneity. Okay, and so we'll talk about what that is. So we are going to pause because it's really loud outside. Okay, so we're going to be able to basically perform, by the end, a chi-squared test for homogeneity. And basically what that does is it gives us information of whether or not a distribution of a categorical variable differs for several populations or treatments. And in the example, I think it'll make more sense to you. We will also be reviewing a couple things like what conditional distributions are. So if you don't remember that was from quite a while ago, make sure you go back and refresh that before you move on. And we'll also have to enter matrices into the calculator. So all sorts of things that we're going to do today. So let's get started. Number one, what does the chi-squared test for homogeneity test? So in this test, we compare the distributions of a single categorical variable, but in two or more populations or groups. So remember that the two sample z-test, we were comparing two different proportions from two populations that we were testing to see if those two populations were the same or different. And so it turns out that a two sample z-test is actually exactly the same as a chi-squared test for homogeneity if you only have two populations that you're comparing. But if you add more populations in there, then you can no longer do the z-test. So you have to do the chi-squared test. So that's kind of the main reason that we do this. So how is the test for homogeneity different from the goodness of fit? Basically, the test for homogeneity has one variable, like color, and it tests color over several different populations. So for example, in the M&M example, in the M&M case, a test for homogeneity, we might have our color distribution in the regular M&Ms and the peanut M&Ms and the peanut butter M&Ms. And we would want to see if the color distribution is the same for all of those different types of M&Ms. So they're all different populations. Goodness of fit takes one variable and only looks at one population. But the distribution, like, you have several different colors. And so instead of comparing two colors, you would be comparing 6 colors or 5 colors. So we're going to move on to the example, and I think just working through the example will be really helpful for you. So I'm going to start by doing it by hand, and then I'm going to show you how to do it as well in your calculator. Okay, so we're looking at the issue of depression, and we're looking at St. John's wort versus other options. Okay, so you have an article that reports they're trying to test if St. John's wort is effective or not in treating depression. And so the study involved 388 subjects who were being treated for major depression. The subjects were randomly assigned, got that, to receive one of 3 treatments: St. John's wort, which is what they're looking at, Zoloft, which is a typical depression medicine, or placebo, and they give it to them for 8 weeks. The table below summarizes the results of the experiment. So they give you this two-way table comparing the response to the treatment, full response, partial response, or no response, and then you've got the 3 different treatments. And the first question says, calculate the conditional distributions of the type of response for each treatment and compare the distribution of response for each treatment. Now remember, conditional distribution is only looking at one of your variables and finding the proportion of in each category for that particular variable. So in this case, they want to look at the type of response for each treatment. Okay, so what you're doing is you're looking at St. John's wort all by itself, and you're saying, okay, how many out of the total, or what proportion out of the total, gave a full response to St. John's wort? How many give partial at St. John's wort? Okay, and then you look at Zoloft separately, and then the placebo separately, and then obviously your total, which you don't really need to calculate. Anyways, so I would recommend pausing at this point before I fill in all of the data, and you try it on your own first. So now what's interesting about calculating the conditional distributions here is that now you can say, okay, using people taking St. John's wort had 29% of them had a full response. Only 25% of the Zoloft people had a full response, and 32% of the placebo group had a full response. Interesting that the placebo had a higher effect than the other two. So, and then you can start, you look at that for the rest of the data. And so what's interesting about that is then you can start asking, okay, well, are these numbers different enough to say that there is truly a difference between St. John's wort, Zoloft, and the placebo? Or is there not? So that's what we're going to be testing with the test for homogeneity. Okay, so then the real question is there a significant difference in the responses under each treatment? And so for this, we're going to perform a chi-squared test for homogeneity, which I will walk you through the steps. State, plan, do, conclude. Same as usual. Okay, 1. State what you're going to do. We're going to perform a chi-squared test for homogeneity, see if there's a difference in response between the depression treatments. And then you want to state your hypotheses. Null hypothesis is there is no difference in the distribution of the different treatments, and our alternative hypothesis is that there is a difference. So there's your null and alternative hypothesis. Next, we want to plan, which is checking our conditions. Oh, don't forget to include your alpha level. Let's add that real quick. Okay, so our first two conditions are random. Were the samples that we took random? Yes, they were. Or were the treatments assigned randomly? That is also another question that you have to ask. And then the independent is your sample less than or equal to the population, or was each trial conducted independently? So in this case, it makes the most sense to say that the treatments were randomly assigned, and that one person's response to a treatment should be independent from another. So, cool. Remember, for the chi-squared test, the third condition is not normality because the chi-squared distribution is not normal. It is skewed, so we need to just test for a large enough sample, which means we need to calculate all of the expected values for every single, basically for every single one of these entries over here, there's going to be an expected count that we need to calculate. All right, so for the expected values, you have to go back to your table, and all of the black numbers are my observed values, right? That's what I actually got in my sample, and so I need to actually calculate what I would expect if there was no difference, right? If the null hypothesis were actually true. So I'm going to calculate my expected values in red, just so you can see the difference between the two. So here's how it works. If St. John's, Zoloft, and the placebo were not different at all, then we would expect, choosing the exact same sample, we would expect 91 out of the 338 to have a full response. And they just happened to be placed in, St. John's just happened to have 27 of them, and Zoloft just happened to have 27 of them, and the placebo just happened to have 37 of them in the sample, right? But so we would expect in each group that same percentage. So 91 out of 338 is what we'd expect in each group. Okay, so if there's no difference, we expect 91 out of 338, which is 26.9% of people in each group to have a full response. Now keep in mind, St. John's group had 113 people, so we need 113 times 26.9% to figure out our expected value for the St. John's full response number here. So right there I'm going to do 113 times 0.269. We'd expect the same percent in the Zoloft group, so 26.9% in the Zoloft group, but our sample was smaller from that group, so we need 26.9% of 109 people for our expected Zoloft full response. So then we get those expected values. Then we need to do the same thing for the partial response. So again, partial response. We expect 55 out of 338 to have a partial response if every single treatment was the same and they just happened to be dispersed into those groups randomly such that St. John's happened to have 16, Zoloft happened to have 26, placebo happened to have 13. Okay, so which means we'd expect 16.3% of 113 to be in the St. John's wort group, and so on. I would recommend you pause it, try it on your own first, and then check your answers. So then we just want to say something like, since all of the expected values are greater than 5, then this condition is met. Alright, next is the do step. Okay, you need to calculate chi-squared, figure out what your degrees of freedom is, which is a little different than in the goodness of fit test. And most of the calculations you're going to be doing on the calculator. So get that out. Okay, so in reality, as far as showing your work is concerned, for chi-squared, all you really need to do is show that you really know what the formula is. So you want to do your observed minus expected, squared, divided by expected, and then add all of them up. But you don't have to write all of them out. So like the first one or two plus dot dot dot, and then the last one should be good enough. So the first term I get is 27 minus 30.4 squared, which I get from this first set of numbers, my observed minus expected, squared divided by expected, and then I do that again for the next one, 27 minus 29.3 squared all over 29.3, and then I do plus dot 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 plus the last one, 66 minus 65.9 squared all over 65.9, and then we use our calculator to actually find it. We'll do that in a minute. Next is your degrees of freedom. This one is a little different than the goodness of fit test. In that one it was just the number of categories minus 1. In this case, you have categories and you have two different sets of data. So you've got your full response, partial response, no response, and then you've also got your 3 different treatments. So your degrees of freedom is actually the number of columns minus 1 times the number of rows minus 1. In this case, that would be 3 minus 1 times 3 minus 1, which is 4. Alright, so to do all of this in our calculator, we have to enter our observed values into a matrix, and then our expected values into a matrix. So I'm going to go into second matrix, and then I want to edit, and I'm going to make my first matrix a 3 by 3, and then I enter all of my observed values. So as you can see, I've entered all of the observed values, which were the black ones, the black numbers over here, into matrix A. Then I want to do the same thing for matrix B, so I go to second matrix, edit. I don't want to edit matrix A anymore. I want to edit matrix B. Again, I'm going to make it a 3, which is the number of rows, by 3 columns. Okay, and then I enter my expected values, so the red values, 30.4, 29.3, 31.2, and so on. As you can see, now I have in matrix A my observed, and in matrix B I have my expected values. So I want to perform a chi-squared test, so I go to Stat, Tests, and then I look for the chi-squared test, which is C, and then I'm putting my observed was in A, matrix A, my expected was in matrix B, and then I calculate. And now I have my chi-squared value is 8.7, my p-value is 0.068, and my degrees of freedom is 4. So now I go back to my paper, and I just need to include all those numbers and then conclude in context. And since our p-value 0.06 is greater than our alpha level, we will fail to reject the null hypothesis. So in our conclusion, we want to say something like, since our p-value is greater than 0.05, our alpha level, we fail to reject the null hypothesis. We do not have sufficient evidence to conclude that there is a difference between the St. John's wort, Zoloft, and placebo treatments.